Thank you. Actually, I would like to take the opportunity first to also thank Sarah and the organizing team. It's a very kind invitation. It's a very nice event. I would also thank the speakers. I think we've heard already quite some amazing talks. And I would also like to thank you for being here and for being such an amazing audience. So give a round of applause to yourself. All right, and before I actually start now doing my job, I want you to do a little exercise because I have seen this before and I think it worked quite nicely. So we will do a little warm-up, and the task is quite simple. When I say science, you say slam. You think you managed that? When I say science, you say slam. Let's try it out. Science, slam. Science, slam. All right, not bad. But it's going to be louder. Science, slam. Science, slam. Yes, that's what we're talking about. Science slam. Actually, today we're going to talk about Panta. Anyone ever heard Panta? Actually, it's Greek. I thought of something geeky, but then maybe, if not geeky, then at least Greeky. No, really Greece, I mean, it's a country, we blame it, and we try to take our money back, but we actually took a lot of it's the origin, it's the cradle of ancient philosophy, and there were so many things we received from them, and we should be rather grateful for all this, and now think also of the Greece workers and so forth, and acknowledge them. And you know, it's all, we are all one community somehow, one scientist community. But Pantari, so it's Greek, and it means everything flows. And I will show you tonight that everything flows also in my discipline, which is systems biology. But you probably never heard of systems biology. What's that kind of thing? So I'm first going to introduce it to you. So on the one side, there's the biology, right? Which is like all the flowers, previous flowers and insects we have seen, and the nice rabbits and foxes, you know, the thumper probably from the Bambi movie. And it's all quite nice, and but this is only one aspect. And then there's a completely different world, which is also my origin, which is mathematics and all those different equations and the computer you use to apply them. And where I study and what systems biology is actually, it's happening at the intersection between biology and mathematics. And you probably also appreciate the Irish flag here, like it's green and orange and white in between. But systems biology is happening right in the middle. So mathematicians would probably say this is an empty set. Or, I mean, because there is no real intersection, is there any? Or biologists would say, well, this is at least a niche, a habitat where we can bloom and blossom, right? Where we have some open space for open science. But this is actually where systems biology is taking place, like where the biology meets the mathematics. And this is what we're going to talk about tonight. All right, so now you got my 2 cents on systems biology, but what is that is flowing here? And to introduce you to that, I will show an upcoming slide that might be offending to some of you. So in case you don't want to be offended, just look away, because where I'm from, rural area, Thuringia, former GDA, parents are communists and farmers, we do home slaughtering. And as you can see from the picture there will be blood. This is pretty much what I talk about tonight, because blood mainly constitutes of red blood cells. One of them you can see here. Red blood cells, or in short, RBC. You know, biology is full of abbreviations, but I only want to use one acronym tonight, which is RBC, which stands for red blood cell. You think you can keep this in mind? All right. First, mathematicians will appreciate, I will give you some numbers on the RBCs. They are very small. In fact, they are just 7 micrometers in diameter. You probably know this sign here. I know it very well. It means average. So on average, they are 7 micrometer, which is the 7 millionth part of a meter. All right. But you have quite some of them, as they are so small, which is like 30 trillion, 3 times 10 to the 13, of those red blood cells in your body. And they, in some, have a weight of more than 5 kilograms. So if you want to save weight, you probably should not save this. And on average, those cells live like 120 days, which does not mean that 3 times a year you have to renew all your 30 trillion red blood cells, but it's a continuous process of renewal. And those red blood cells, I mean, they look nice, they are quite simple. Actually, they are just sacs of hemoglobin, which is the molecule that carries oxygen through our body and all the organs and keep us alive. And those red blood cells, they have also very interesting biophysical properties. You know, they have to be squeezed in order to go through your veins and all the arteries and so. And as you can also see, you can apparently make good science with them. Because, as I said, they are a good model organism, they are quite simple. For instance, nowadays, I mean, you at MBA will appreciate that, we have the technical capacity to sequence each and everything, like the genome of every patient, of every tumor, and we can sequence all those, and we are sort of overwhelmed with all this information. I mean, we hardly can make use of all those A's and T's and C's and G's, but the upside of those red blood cells is they don't have any DNA, so we get rid of this problem at this point. All right, but the way those sacs of hemoglobin are produced is what I call a flow of maturation. And this flow of maturation starts with something that is a buzzword nowadays. I mean, you hear it all over media ever and ever again. That's why I put a hashtag in front of it. It's a stem cell. And stem cells, they have one capacity, which is to self-renew. Like, they are the unlimited source, and they have a second ability to give rise to all other cell types. So they are the unlimited source of all our entire immune system and our entire blood system. Thank you. And if you have them, you're quite lucky. Unfortunately, they are quite rare. But as I said, they are quite capable of doing basically anything. So I was thinking about an analogy, and since we are here at O'Reilly's, I thought of St. Patrick. I mean, if you have him, you would be lucky because he's your saint, and you will be safe once you have him. All right, but as the stem cells then differentiate and give rise to other cell types, among them there's also a progenitor cell. And these cells we usually extract from fetal liver of mice. So here you see a fetus from a mouse, and the red thing in the middle is not the heart, but the liver that is already full of those red blood cell progenitor cells. And just to give you an idea, we need 250 of those mice. We make them like every 2 weeks, and from them we get like 20-25 pregnant mice. And from those we get, say, well, 120 fetal livers, and from those we only get like a couple of million of those progenitor cells, so they are still quite rare. But in the end, as they further mature, they get rid of their DNA, as I already said, and then they form those red blood cells. And again, we start at very few stem cells, and we end up with 30 trillion of those red blood cells. So we need to have a massive amplification from this very rare source here until this vast ocean of blood. And what I picked it here, I rotated it, it's the River Shannon from Ireland, you probably know. It goes through Limerick, beautiful city, you probably also know from Angela's Ashes. And then you end up in this ocean of blood here. And in order to understand this process, how those cells are generated and how this massive amplification takes place, we need some math, we need some rational interference, because what we want to do, we want to understand this process and manipulate it to create blood artificially and to, of course, cure some disease, hematologic disease and so forth. Alright, here's a microscopy picture of those progenitor cells. I stained the nucleus because they still have their DNA. I stained it in red. And since it's kind of a bit of a problem to remain silent for you, I appreciate that. I have some instruction for you. To encourage you something, it will be a visual instruction. And just watch the image carefully, you will get the instruction, and then just do what you've been told or what it suggests. And if not, I mean, I will just tell you and then you do it. Alright, so here we have the cells, and now what happens now? Make some noise! Alright. Anyways, so just some random interruption. So we start with those progenitor cells, and in order to form many of those red blood cells, there's many cell fate decisions that have to be made. Among them, there's of course survival. The cells have to survive. They have to proliferate, which means they have to increase in number and duplicate and multiply. And they have to differentiate, which means they further specify their functions and then finally form the red blood cells, all right? But the way this could happen, I mean, of course, there's a certain hierarchy among those decisions. So start with a very simple example. say we have only one of those progenitor cells and we want to have many of those erythrocytes, then one option would be that those progenitor cells first proliferate and form many progenitor cells, and then they undergo differentiation and form those red blood cells. The other option would be that, of course, the progenitor cell first differentiates, and then those more mature cells proliferate and increase massively in number to form many red blood cells, all right? So we have these kind of two opposing hypotheses we have to now investigate scientifically. All right, and the technique we use for this is also something that flows. It's called flow cytometry. And the principle behind is quite simple. We have all our cells in a multi-well plate, so in all those different holes we have our cells. We can extract them, of course, first to treat them under different conditions. We extract them, and then they are like on a water slide. Thank you. They are on a water slide, on a thin liquid stream, and one after the other, in a chain of pairs, they are passing a laser. And on top of the cells, they are carrying some kind of ID card, so we can also identify them as progenitor cells. And this is basically what's been detected here at those detectors. And since this graphical visualization is all nice, I thought probably still you could hardly imagine how this works, so I have some kind of illustration, and therefore I would like to ask Sarah to come on stage. So please go fix the bucket with your feet. Yes. And hold this up to me. Alright. And guys, now I know it's going to be tough, but please just look on the tube, not on her. So here I have my blood, right? And now I'm going to fill this into this tubing. And then there comes the laser. And this is pretty much how flow cytometry works. Thank you, Sarah. One applause for Sarah. All right. But speaking of flow cytometry, so we now had this flow of maturation with flow cytometry, but actually there's another thing that could flow. It's the flow of words. And you know where Science Slam originates from? It originates from Poetry Slam. And Poetry Slam itself roots in, sorry, it was too early, but we can then tune up the music a bit. Poetry Slam itself roots in rap music, alright? So listen up. Music up, please. Everything goes, everything knows what really goes when obviously grows, cell cycles, so by the net proliferation, power plant signaling, terminal maturation, and systems biology. I found my personal mission to disentangle the process of a cell-fate decision. I throughput techniques that we call deomics are not as simple as in the funny PhD comics. It's not intuitive, that's why we need the math. And in the aftermath of the biology found the math, we got to know ourselves and thus know ourselves. And the lesson to learn is, no one needs to be concerned with her or his thesis. We need patience. Combat cancer with equations. For the patients, now you. Combat cancer with equations. We need patience. Combat cancer with equations. Alright, thank you. Not too bad. Hold on. Please, focus. This is one of those equations. Looks a bit complicated, but no worries, I will guide you through. So, it's actually called the differential equation, which means it always describes the change d of something. In this case, the number of our actual progenitor cell type we are looking at. I cannot see you, so. And this the number of progenitor cells now changes with time t. All right, and if we want to describe
Тихо! А ну тихо!
Sorry. Anyways, this number of progenitor cells changes based on the proliferation rate, which I call A. And of course, you have less cells if more and more cells differentiate into another progenitor cell type. And of course, these rates are multiplied by the actual number of cells you have, because the more cells you have, the more can proliferate and the more can differentiate. As simple as that. And plus, you get more cells if there are actually other progenitor cells to differentiate into this very same cell type you're looking at. I think it will become more clear when we look at such a model, which I depicted here. So, for instance, the change of the number of these progenitor cells here, N2, changes with T, and it gets higher when they proliferate with A2. They get less if they differentiate into N3, but they get also more if those cells N1 become N2, right? So it's kind of very simple. But actually what we want to find out now is the values for those rates here, for those proliferation and differentiation rates, because then we could identify the actual hierarchy of our hypothesis or of the cell fate decisions we want to investigate in the first place, right? Here's another equation. I already told you this. Systems biology is like the combination of quantitative data generation with the mathematical modeling. And here's how the actual data looks like. So what we did basically, we cultured those progenitor cells, and then at different points in time, we count the total number of cells, here million per milliliter, and then we also, with flow cytometry, we determine what the fraction of the different progenitor cells is. Silence, please. Thanks. All right, and the question is now, is there actually a set of those different rates that can describe our experimental data? And the answer is yes, there is. So we can describe this kind of experiments, but what can we now actually learn from those rates when we look at the actual values? Well, in fact, when we look at them, we see that there is an initial wave of proliferation, but that's not merely it, because, I mean, of course, afterwards there is some differentiation, but there's also a second lower wave of proliferation. So it's not a one or the other, or one after the other, but both decisions are sort of mixed. So when we look at our initial hypothesis, whether we have first this proliferation and then differentiation, or first differentiation and then proliferation, we have to say it's not as simple as that. We probably have both happening at the same time. So when we then take a step back and revisit the original title of the talk, Panta, rhei, everything flows in systems biology. When now looking at that, we probably have to rephrase it a bit. We have to say everything flows, and that is why we need systems biology. Thank you.